Okay. I should just comment, I think, already heard me try to say this, is to try to avoid memorization. The last time I taught this class, students tried to memorize everything. The memorization worked, I think, close enough for many students up to Calc 2. But in Calc 3, there are just going to be too many pieces to the puzzle. It's going to be hard to keep track of memorizing everything, right? So I think I would say that students in up to Calc 2 can be rather successful if they're very good at memorizing things. And memorization is often used as a way to compensate for understanding. But I challenge you now to, or rather warn you first to say that there's too much stuff to memorize in Calc 3. And therefore, because of that, I suggest you work on understanding instead of memorization. And I will say that it is doable. Like you have to work on understanding, but that's going to be necessary, and it's the only thing that I can think of that's going to be sustainable. Calc 3 requires some odds and ends that don't get used very much elsewhere. Things like vectors and parameterization and lines and planes and so on. Those are not the end goal. We will just use all of these pieces. These are going to be all little mini pieces, mini tasks to a bigger task that appears in the last chapter. So nearly everything that you've ever seen in algebra, trig, geometry, calc 1, calc 2, and some of the new things we're looking at will all make an appearance later on in calc 3. And so it really becomes too much to handle. I had to have an intervention around the third week of the semester last time I taught this class, and I thought I'd just include that information kind of earlier on without having to feel like you don't have to feel bad about it. It's just you really, this class is not going to work trying to just memorize everything. So please work on understanding. It's just too much stuff to memorize. There's so many individual procedures, and within a procedure, there's so many pieces that look similar to other procedures. So it's good to know how to use each thing separately, right? It's sort of like if you cook enough recipes that use oregano, you got to kind of just know what oregano does at some point, right? So that's kind of the idea. Okay, in Calc 3, I think everything, in fact, only really works because you need to know how all the little pieces fit together. Okay, so let's try this. This is a problem that I don't want you to memorize the process for. I just want to say that a lot of um, the pieces of the puzzle are all here already. So I have the point 0, 0, 1, the point 2, 0, 0, and the point 0, 3, 0. And so 3 points, if they're not collinear, are going to form a plane. So there's a plane that goes through these 3 points. Let's find an equation for that plane. So the picture I would draw looks like this. You just create a vector from, say, A to B and a vector from A to C. You could make some other choices. But once we created those two vectors and we cross product those two vectors together, we'll get a normal vector. And that's a thing we need, right? We need a normal vector for this plane. So let's go through that, right? So the vector from point A to point B would be 2, 0, -1. Just do the subtraction in the correct order. And here's the vector from A to C. We'll take the cross product of these two vectors. I skip the work, and you'll get the vector 3, 2, 6 from this. Cool. Now that we have this normal vector, 3, 2, 6, now following things that we saw earlier, all we needed is a normal vector and the generic vector, right? So we need, how do we get the generic vector? Well, that was a generic point minus specific point, meaning we need a specific point, and we actually have 3 specific points. So you take your pick. I'll use 0, 0, 1 to be x naught, y naught, z naught. Okay, so then the generic vector is, so the generic point coordinates are x, y, and z, and then the specific points coordinates are 0, 0, 1, so you'll see after the minus sign 0, 0, 1, and if you just simplify slightly, we have the vector x, y, and z minus 1. So this generic vector, which is just sort of a vector, just any vector that starts at A that's just being drawn in the plane, should be dotted with 3, 2, 6. And of course, because these vectors need to be perpendicular, that dot product should result in the scalar 0. So this is all we do. Just the normal vector that we just computed earlier, dotted with this generic vector, should be 0. Write out what that dot product should do, component-wise multiplications, and add the results. And if you do just a little simplifying of this, you can rewrite this as 3x plus 2y plus 6z equals 6. You could have picked the fixed point to be the b point instead, in which case the generic vector would have looked a little different. Instead of x minus 0, y minus 0, z minus 1, you'd have x minus 2, y minus 0, z minus 0. So the x in front of the minus signs, x, y, z as before, after the minus signs 2, 0, 0, because those are the coordinates of B. And if you work this out, same sort of deal, like this is just an alternate answer. Take the normal vector from earlier, 3, 2, 6, dot it with this generic vector right here, right, x minus 2 comma y comma z. And if you simplify, or if you perform the dot product here and then simplify, you again get 3x plus 2y plus 6z equals 6. So for the previous question, notice that both of those routes led to the same scalar equation. Now let's think about this neat thing. Just how we just got 3x plus 2y plus 6z equals 6. How would you describe 3x plus 2y plus 6z equals 7? Notice the left sides are the same. Well, first of all, what kind of shape? It should be a plane. And then second, how do the normal vectors of these two planes relate? Well, this equation is for a plane, and this equation is for a plane, and both of those planes, as we read off the coefficients to the variables, both of the normal vectors are the same. So what can we say about these two planes have the same normal vector? It's because these two planes are they're technically different, but they're very similar. They have the same normal vector, right? So the two planes are parallel, aren't they? There's no point that is on both planes. They really are truly parallel and not the same plane. Like they're spaced apart from each other, because if you had a specific point that satisfied, you have an x, y, z that satisfies that this combination equals 6, then it's also those same values of x, y, and z aren't going to equal 7. So these are two parallel planes with a gap in between them. Let's find a point on the plane with equation 3x plus 2y plus 6z equals 7. Again, there's many possibilities. You just need to make some choices. I just happen to choose x equals 0 and y equals 1, but you can make other choices. And when you do that, you're going to end up with a 0 plus 2 plus 6z equals 7. So you can solve for z and get z is equal to 5/6. Therefore, 0, typo, 1 5/6 is a point on the plane whose equation is 3x plus 2y plus 6z equals 7.